Guys, okay, so now that's the one thing that's our variable, the sine of x. So we would, in our algebraic equation, add 1. So we're going to add 1 in our trig equations. The sine of x is going to stay together here. Then in our algebraic equation, we would divide by 2, and we would get our answer. In our trig equation, we'll divide by 2. We keep the sine of x together, and we're done with the algebra part. But now we're stuck with the trig part. We have, this is the best part. We have an angle whose sine is 1/2. So the first thing we're going to do, and no restrictions, is say, where is sine positive?
1.
And y, sine uses the y. 1 and 2. So sine is y over r. What angle is this over here? 30. So this guy is 30 degrees. What is this guy? 150. So I'm going to work it in degrees just so that you see it for a second. So we have 2 angles that make this true. Now, this is an equation. We can absolutely test this to see if it works. We can come back to your original thing and say the sine, 2 times the sine of 30 minus 1, hit enter, and it should say 0. Then we'll check 2 times the sine of 150 minus 1, and it should say 0. It's an equation, so you can check it. Now, if we leave this in radians, then this guy is pi over, how many times is 30 going to 180? 6. And if this is 6 pi over 6, what is this guy? 5 pi over 6. God bless you. Thank you. So we had 2 solutions to this. You're going to treat it like a regular equation, but then it's going to say the sine of x, the cosine of x, the tangent of x, the secant of x. Whatever it says means we have the trig part now. We have an angle whose sine is. Now, you can't just pick up your calculator for this, because this is not restricted angles. Okay. So does this make sense? Don't stop here and tell me you're finished, because we got all this to do yet. We got the trig part to do. Yes. Yes, let's try it. Let's pull up our calculator. Put your calculator in degrees if it's easier for you, or if you're solved it in radians, put it in radians. I'll put it in degrees just so that we can put it in and see what the angle looks like. So we're going to say, just like you read this, 2 sine of 30, watch your parentheses because you have to close your angle. Minus 1, when I hit enter, it should say 0. Then I'm going to do 2 sine of 150 minus 1, and that should say 0. So I checked my answers. Don't you check your regular algebraic equations? Don't you put this back in for x? 2 times 1/2 minus 1. So there's your 1. Right? So I don't need you to do a formal check. Just go throw it in your calculator. Throw it in your calculator and check. And easier, do it once, do second enter, do it again. It works. Okay? Not so bad, right? All right. Now, we're going to work on this part for a second. This says, let's take this equation. This is my variable right here. I'm gonna take this out for now, and I'm gonna put a little x in it for a minute. It's gonna say x plus radical 2 equals negative x. How would I solve that? Subtract x. I don't want to add x to both sides. You can, and then you can subtract your radical too. But right now, I'm going to leave it like this. Okay, good. Let's do with the word sign in there. Did somebody have a question? Did I hear a question? No? Okay. I stopped because I thought I heard somebody ask something. So, same process. You don't want to add sign here. If you did, you just would subtract your radical 2 later. But you want to get rid of this sign and combine it with that one. This is your variable. There's my variable still. So how do I want to solve for my variable? If I'm up here, what am I going to divide by? Negative 2. So I'm down here. I'm going to divide by negative 2. So I get the sign of x, this is still my variable, is equal to negative radical 2 over 2. Does that sign look familiar? Yeah. What angle is that has the sign of radical 2 over 2? 45. If you want to unrationalize it, you can unrationalize it. But we know now what our angle is, don't we? We just got to see where do we locate this. So on our 4 quadrants, in our 360 circle, where's sign negative? The 4th quadrant and the 3rd quadrant, wherever y is negative. So let's just fill out one of them. Y over r, so you guys told me this was a 45-degree angle. So let's name this in radians. 45 goes into 180 how many times? 4. So this is going to be 4 pi over 4. This is going to be 8 pi over 4. So x is equal to what? 1 more than 4. 5 pi over 4. And x is equal to 1 less than 8. 7 pi over 4. Okay, now, way back when we first started to do angles, we said we found coterminal angles, angles that terminated at the same time. We found more angles because we said not only does it go around 360, doesn't it keep on going around and around and around and around, right? Because isn't your sine curve and your cosine curve endless? So they technically go around and around and around. Now, when we find all solutions to something, all solutions means this. In my realm of 2 pi or 360, I have 2 angles that make that happen. But my circle keeps going around and around and around. And a circle is worth 2 pi. So if I take this, and let me just put a little color in here. If I take this side, and I went to here, and I want another one, don't I have to come around from here another 360 degrees, or another 2 pi, then another 2 pi? You want to bring me back to that again? Then another 2 pi? So to make all solutions, we're going to say x is equal to 5 pi over 4 plus 2n pi, where n is any integer. Because if I go around 0 pi, that means I'm just at that angle. If I go around 2 pi, I added 1 circle, another 2, another 2, another 2. And I'm going to do it for this guy. This is my all solutions. Okay, does that make sense? We located the 2 in 2 pi, but we have to keep adding 2 pi to them because there's multiple, there's many, there's endless solutions. Endless solutions here. Good? Now, the other part of it says, what if I just wanted you to go from 0 to 4 pi? So in 0 to 2 pi, how many solutions did I have? In my original circle, how many solutions did I have? How many triangles do I have?
2.
2. So in 4 pi, I should add how many more?
2.
2 more. So I should have 4 altogether, right? Now, if you're only going to go to 4 pi, sometimes life is a little easier. You're going to say, okay, this guy's 5 pi over 4. This guy's 7 pi over 4.
So 13 pi over.
So therefore, if I add another 4, what is this guy? This is 8. What would this guy give me? 12. Just think out loud for me. 12. And what would this guy give me?
16.
So now, Monasia came up with 13, because isn't it 1 after the 12? So this will also have 13 pi over 4. And what will this one have? 15 pi over 4. Good. Could I do that? Everybody wake up with me. Come on. Hang in there. I could do that. I'm only going to 4 pi. Or I could say, take this guy and add 2 pi to it. Just keep adding 2 pi until I hit my 4 pi. So here's the key. See this denominator? Convert this denominator into the same thing, fourths. If I multiply this by 4, I multiply this by 4. This is where I'm going to stop. Now, I'm going to take my 5 pi over 4. I'm going to add 2 pi. But I also need that in fourths, because in fractions, don't I need a common denominator to add? So if I convert this to fourths, what's 4 times 2? So I have to add 8 pi to the top, because now aren't I adding the same common denominator now? So I start with 5 pi over 4 and I add 8. What do I get? 13 pi over 4. Okay? Now, if I add another 8, I'll be at 21. Oops, I needed to stop at 16. That's that part. Then I come down to this guy, and what do I add? 8 again. 8 pi again. If I add 8 again, I'll be at 23. I'll be out of that, right? But make it make sense. If I have 2 and 2 pi and 4 pi, I'll have doubled, 4. Make sense? Okay. Not so bad. We have all solutions. This is how I say all solutions. It's generic. This is how I define from 0 to 4 pi, from 0 to 6 pi, from 0 to 8 pi, whatever it is I'm looking at. If it's only going around one more, and you already put them down there and doubled it, I would just keep that little system going, just like Renasia did. I would do it that way. If you want to do it this way too, absolutely. When you get a lot of angles, do it this way. It's easier. All right, let's take a look at another one. Is this the last? We've got a couple more. Okay. Now, what's my variable in this guy? Tangent x. So if I looked at this, what's the first thing I need to do? Subtract 3. Good. I got to get this isolated. So I'm going to subtract 3. Remember, this is my variable. And now what do I want to do? Divide by 3. Good. So tangent x is equal to -1. And that sounds vaguely familiar to me. So where's tangent negative? 2, 2 and 4. And tangent is 1 over 1. What reference angle is that? 45. So if this is 4 pi over 4, and this is 8 pi over 4, what's your angles? One before the 4, 3 pi over 4, 1 before the 7, I'm sorry, 1 before the 8, 7 pi over 4, sorry about that. Now, that's how many I get in 2 pi. If I'm looking for all solutions, I normally say plus 2n pi, plus 2n pi, plus 2n pi. But tangent, the period of tangent is only pi. So it repeats itself every 180 degrees. Where the other ones repeated themselves in a period of 2 pi, every 360 degrees. So now, watch up here 1 second. If I'm here at this one, I come from here, I terminate right here. How many degrees do I have to add for it to terminate right here? Straight across the circle. 180. So now, all I have to do is take this guy and say plus n pi, where n is any integer. I don't really need to say this guy, because the period of pi is every 180 degrees. Every pi radians. You have this. I can give it to you, thank you.
So it's 4 pi.
So if I take 3 pi over 4, and I added this, this would be 4 pi. Aren't I adding 4 pi to get 7? I'm only 180 degrees away, because my period before was every 2 pi. Now I'm just every pi. So if I'm only going to work with this guy, plus n pi. I'm going to go to 4 pi. What denominator do I want to convert this to? 4s. So this is where I'm going to stop. This tells me 16/4, which is 4 pi. This is where I want to stop. I'm going to convert this denominator to what? 4, because when I add my fractions, I want a common denominator. So I'm going to keep adding 4 pi to my 3 pi, and then whatever it is. So this makes sense, because if I add 4, what do I get? 7, which is where I was. Add 4 again. 11. 15. And if I added more, I'd be out of that range. But if I only had 2 and 2 pi, how many do I expect to get in 4 pi? 4. If I have 2 and 2 pi, which is 360 degrees, and I add another 360 degrees, I come around one more time, how many more angles should I get? 2 more. So altogether, I should have 4. Don't I have 4? Now, I know the all solutions, and the 0 to 4 pi is what's new. That's the new part. All right, see if you can solve the next equation. See if you can solve this. Yeah. See if you can solve this for me. This would be looking like, whoops, oh, what happened there? Right? This tangent x is my variable. But it just so happens it's squared. What would I do to this guy to solve it? Add 1, then divide by 3. Oh, square root. So then I would get a plus or minus. Radical 1 over radical 3 would be plus or minus 1 over radical 3. Do the same thing with the tangent in there. Same problem. You're going to take the square root of tan just like you took the square root of x. It's just going to come out to be tan x. So you're going to add 1. You're going to divide by 3.
Wait, that means that you can get this in every quadrant.
Every quadrant. Yeah, absolutely. Every quadrant. We're going to get 4 solutions. Very good. So when you undo a square, you get a plus or minus. Separate your radicals, otherwise you're not going to recognize this as your special right triangle. So separate your radical. My board froze for a second. And just like when I just said, you're going to get this in every quadrant. Watch. Get your plus or minus, separate your radicals. If you leave it like this, it's not going to make much sense to you. So separate them. So now your tangent is equal to plus or minus 1. Don't those look like part of my special right triangles? A 1 and a radical 3? Which side is missing?
The 2.
2, right? So I've got all 4 quadrants to use. So tangent is y over x. Oh yeah, this so looks like my special triangle. What reference angle am I? 30. Now, watch what happens. This guy is straight across 180 away from this. So if I name this angle, and what's this angle, this first angle, in radians? Pi over 6. If I add n pi 180, won't I come to this angle where that terminates? Plus n pi. Then, I did those two. I got to get the two opposite of these guys. If I name this guy, this is 6 pi over 6, so what's this guy called? 5 pi over 6. And if I go 180 away from him, I'll hit the other ones. And there's your all solutions.
Wait, are we supposed to have 4?
You do, but I didn't ask you to find it from 0 to 2 pi. I asked you just this time to find all solutions. Endless. Endless. Every unit circle you make, you'll find 4 answers, right? So you'll have a number of infinite answers. So how do we say all solutions? This is how we say all solutions. If we were going to go from 0 to 4 pi, how many solutions would we have from 0 to 4 pi? 8. So let's throw in 0 to 4 pi. If I'm going to go from 0 to 4 pi, your bottom number that we're going to convert to is what?
16 pi.
So it'll be 16 pi, or 24 pi, 6, because we're going to do 6s this time. So this time we're going to add 6 pi. So what? Pi over 6, add 6.
5 pi over 6.
Add 6 to this guy. 7 pi over 6, 13 pi over 6, 19 pi over 6, and if I add 6 again, I'm out of my 24. Do it to this one. 5 pi over 6, add 6. Yeah, that was the other one we found. Keep adding 6. And didn't we expect 4 of them in 2 pi if we did this? 4 and 2 pi? 8 of them in 4 pi? Right? But all this one asked for was all solutions. Make sure you qualify it somewhere with n is any integer. Okay? That's the part that's different for you this time around.